Hi, everyone. Congratulations, you've made it to the last lecture of the semester. This is section 5.5 on substitution. After this, your only responsibilities will be making sure that you have the last homework done and taking your final exam. So, congratulations this far. I don't know any of you yet, actually. So, these videos are all completely pre-recorded. I'm finishing this one up 2 days before our semester is starting. So, I have not met a single one of you yet. So, I'm sure that by the end of the semester, I'm going to miss you all so much. I have yet to learn your names so far. Um, so I'm sure that I will miss you all. Um, I tell all of my students if you ever need me in the future for any math help or anything at all outside of math, even, feel free to just shoot me an email. I'm always here. I'm always willing to help. If you are on campus, I do have an office on campus, so feel free to shoot me an email and I can tell you where I am. I'm always around and I'm always willing to help. So anyway, this is our last lecture. This is substitution 5.5. All right, so this is a little refresher. We've already seen this table before. This is our differentiation formulas and our indefinite integral formulas. So this is a little refresher on what the different indefinite integrals may look like given different setups and integrands. Now we can get into exactly what it means to substitute using indefinite integrals to start. So substitution with indefinite integrals. First, we want to let u equal the g of x. So we want to determine some g of x, and we're going to call it u. And we specifically want to choose a g of x where we can find a g prime of x that's continuous over the interval, because we want the integral of f of g of x times g prime of x to just give us the integral of f of u. And you may be looking at this and being like, what the heck am I reading? This is very confusing to start, okay? I will give you that. This looks weird. I promise when I show you what I'm talking about, it'll make a lot more sense. Right now, maybe it doesn't make so much sense. But essentially, you want to find some function within your integrand such that when you take the derivative of it, and when you call this u, it gets rid of everything that's in terms of x's, and you're just left with things in terms of u's. And the reason that you want to do this is because sometimes we have functions that we cannot take the integral of using our typical power rule or our typical just knowledge of integration, right? We can't just say, oh, this is only 1 over x. I know the integral of that is the natural log of the absolute value of x. Maybe we have something else going on where we have to now take that into account. So that's the point of substitution here. And you'll know if you need to use substitution based on whether or not it looks like something we can just take the integral of. All right, so then you would integrate this. Obviously, you get the capital F, whatever that would be, plus c. And then the last step, specifically with an indefinite integral, is going to be plug your g of x back in. So the u is really just to make it easier for you to integrate it. And then you want it still in terms of x, so you'll just plug in whatever function back into your f. And again, I know this sounds really confusing right now. Once I show you an example, I think it'll make a little bit more sense. So this method is called substitution, where we substitute part of the integrand with the variable u and part of the integrand with the variable du. I will again show you what I mean. It's also referred to as a change of variables because we are quite literally changing the variables in our function, right? We're going from whatever the variable is to u. So this is how we're going to do that. First of all, we want to look carefully at the integrand and select a g of x with the integrand to set equal to u. But we don't want to just choose some random g of x. We need to choose it carefully. We want to select the g of x such that g prime of x is also part of the integrand. So if you look at something and you think, hey, if I took the derivative of that, I see that in my integral as well. That is the thing you want to have as your g of x. If you find something and you're like, oh, that derivative is nowhere to be found, that's probably not something that you would want as your g of x. It would not help you in the slightest. All right, set that equal to u, and then take the derivative. So we would say du equals g prime of dx. This is kind of a little throwback to differential. So what you remember is du dx is equal to g prime of x, right? But using differentials, we know that we can separate the dy and the dx. So that's where we would, or the du here and the dx. So you can multiply the dx to the other side, and that's exactly what we're going to have here. So we'll just write it explicitly like this from the beginning, where we say du equals whatever the derivative of this thing was, times dx. My little addition to this is going to be solve for dx, because you want to essentially plug in dx for the dx that you have. Sometimes your dx is going to have some variables or some numbers in it that are very important to the end value that you get. And so it's important to solve for dx and plug that back in. It just kind of helps you not lose track of anything. All right, we should now be able to evaluate the integral with respect to u. If you can't evaluate it, go back and select something else as your u. I'm not going to highlight that because that's just kind of a given. If it doesn't work, you're going to probably try again. That just feels natural. All right, the next step that I would say is evaluate in terms of u. After you evaluate in terms of u, obviously you would have a plus c at the end because it's an indefinite integral. You're going to write the result in terms of x and the expression g of x. So you're just going to take your function and plug u back in, plug your x, whatever it was, back in. All right, so let's go ahead and kind of look at an application of exactly what the heck I'm talking about. So given some integral in which we would want to use substitution, we would first identify that we can't use any other method, nicely at least. So if you look at this, for example, we know that integration is not something that you can like distribute through, right? So you can't say that the integral of 6x times 3x squared plus 4x to the fourth is equal to the integral of the 6x times the integral of the 3x squared plus 4x to the fourth. That's just not at all how it works. You'd get the wrong answer. So then the next step would be, well, can I nicely simplify this to be just an addition or subtraction of terms to use the power rule? And well, theoretically, if you wanted to distribute the 3x squared plus 4x 4 times and then multiply by 6x, you could, and then you could use the power rule. That feels kind of unreasonable. And like you'd be there for 30 minutes just distributing. So naturally, we would want to find a faster way of doing things. And so right off the bat, we would say, okay, this isn't something that I could use my regular rules for. So I need to do something else. Now, of course, in Calc 2, if you were to take that course, you would have a lot more tools to have to kind of sort through. In this class, you either have the regular rule, that's either a power rule or like just a general function, or you have substitution. Maybe the fundamental theorem of calculus, but that's also just kind of the thing that I said before. So there's only two options. So I'm kind of limiting your options here. So obviously we have to use substitution for this. Now that means we have to choose a g of x. So I want some u equal to g of x such that g prime of x appears in this function. Specifically, when it comes to things with just plain old variables, I don't mean trig or anything like that, just variables, your u, so this is an important note, u is 1 degree higher than du, which would make sense if you differentiate something, you drop by a degree. So what I mean by that is if you look at a function and you notice that one term or one factor is a degree higher than something else, and if you took the derivative, you would just wind up with a single variable that is of the degree that you have left, then you're going to use u sub or u substitution. U sub is what we call it. And in fact, that's what we have right here. So you see 3x squared and you see 6x. The plus 4 doesn't matter. You take the derivative of 4, you get 0. So what you see is this 3x squared plus 4 quantity to the fourth. This is kind of the problem right here. So if you take the derivative of 3x squared, what you get is 6x. Well, that happens to be this right here. So you need a u that's equal to g of x such that g prime of x appears somewhere. And it may not appear exactly. So if you maybe have like 12x, that would also be the same thing as like appearing, because it appears up to like a constant or a coefficient, as long as your variables are the same. So that's what we're going to do. We're going to set u equal to the term that's 1 degree higher than the other term. So that's going to be this full 3x squared plus 4. We want to get rid of that whole thing, which tells us that du, so the derivative of this is take the derivative of this, which is 6x dx. Now we want to solve for dx, so dx equals 1 over 6x du just by dividing the 6x over. So these are the two things that we need. We need u and we need dx. And so what we're going to say is that the integral of 6x times 3x squared plus 4 to the fourth dx is also equal to the integral of 6x. Well, we said that 3x squared plus 4 was u, now to the fourth. But dx we have an equation for. So this is exactly why I solve for dx. Some people will leave it at this. I like solving for this because then it's just simply plugging in a value. Times 1 over 6x du. And we, in order to do substitution, need everything in terms of a single variable. So here we have it du, which tells us we're integrating with respect to u. Here we have x's. We cannot have x's with our u. But what you notice is 6x divided by 6x, they go away. And like I said, the constant out front doesn't matter. What would matter is that the x's would cancel out. So if one was a 6 and one was a 7, that still doesn't matter. You can pull the constant out front using the constant multiple rule and just be left with u's. And so what this actually is the integral of u to the fourth du. And so what you've done is now you've taken this thing and you're saying, well, this is actually just u to the fourth. Well, we know how to integrate u to the fourth. That's up a power divided by that power. That is just the power rule. So u put a fraction, up a power is 5, divided by that power is 5 plus c. But this isn't quite the answer because this function wasn't in terms of u to begin with. It was in terms of x's. So the last step is simply to plug back in for u. And so this is the quantity, because this is to the fifth, so you have to put parentheses. So this is 3x squared plus 4, quantity to the fifth over 5 plus c. And that is the integral of this function right here. If you were to look at that function, I would guess you probably wouldn't expect that to be the integral. But using u sub, we now can go ahead and actually determine the integrals. All right, let's go ahead and take a look at another example. Now we have this. Integral of z times the square root of z squared minus 5. So the first thing that you may be inclined to do is maybe rewrite this square root, which this would be a valid thing to do. You may say this is the integral of z times z squared minus 5 to the 1/2 dz, because you identify that we can't integrate or derive a square root. That's a function, not a number. We need a number. So we put a number in. And now you say, well, can I distribute this 1/2 in any way? No, you can't. You can't distribute a 1/2 into this. There's no way of doing that. So we can't use our typical rules to find this integral, which means that we're probably going to want to see if u sub applies. For u sub using simple variables, we again want to see if we have two variables that are the same variable where one is a single degree higher than the other. And in fact, we do. We have z squared minus 5 as one term, and we have a z as the other term. Now, I want to note that it wouldn't work if this 5 had, like, say, just a regular z on it, because then you'd have like 2z minus 5 as your derivative, and things wouldn't cancel nicely. So these questions will be set up so that they work out nicely. So we want to choose u to be the thing with the higher degree and that entire quantity. We wouldn't just want it to be z squared, because then we would still have this minus 5 and we can't integrate that. So we'll choose it to be this entire quantity, z squared minus 5. And then we can find the derivative. The derivative of that is, well, this is 2z, but then we took the derivative, so we have to say it's dz. Now we solve for dz, which is 1 over 2z du. And this is why I write my z's like this, because this could look like 22. Because my handwriting is not the best, as we all have seen throughout the semester. I'm sorry, period. So now we have u and we have dz, and we can plug back into our integral. So this is the integral of, well, we haven't done anything with this z, right? We'll leave that there. Now z squared minus 5 we said was u, so this is u to the 1/2. dz we have as this expression. This is 1 over 2z du. And we know that we can never have two variables in our equation in this course, at least. So what we have to make sure is that the variables will cancel out. So the variables that are not the variable of integration will have to cancel out. Here we have a z and we have an over z, so these two guys cancel out, but you notice we are still left with a 1 over 2, which is okay. So this is equal to the integral of 1 over 2, because I'll pull this out, u to the 1/2 du. And if you'd like, we can also write this as 1/2 integral of u to the 1/2 du. u. So this is a constant multiple rule that says we can pull out a constant multiple and it doesn't change anything. Now we can use the power rule. Up a power, divide by that power. Be careful not to forget this though. Sometimes I'll even forget that when I'm doing this, like it just kind of sits there and then you forget about it. So just rewrite it, multiply by, stick our u in there, up a power, 1/2 plus 1 is 1/2 plus 2 over 2, which is 3 over 2. So it's u to the 3 over 2 over 3 over 2. But plus c, we don't want to have a complex fraction, so let's rewrite this. Something over 3 over 2 is the same thing as that thing times 2/3. So this is 1 over 2 times 2/3, u to the 3/2 plus c. But when you multiply fractions, you can multiply across. So these two will cancel out and you get 1/3 u to the 3/2 plus c. But again, this wasn't originally in terms of u, so we don't want to leave it in terms of u. That would be incorrect. We want to plug back in for u with what we said u was in the first place. So this is actually equal to 1/3 quantity of z squared minus 5 to the 3/2 plus c. And that will be our solution. Again, if you look at this, you probably wouldn't be able to produce this answer just by looking at it. So that's why it is important to use u sub in this kind of a situation. All right, here's another example. This is really just going to be a lot of examples today because u sub is kind of a weird thing to wrap your head around. And so I want to give you as many examples as possible so that you can get a little bit more exposure to it and genuinely understand like what the heck is going on. So what we see here is we have sine of t over cosine cubed of t. And immediately here, it may not jump out to you exactly what to call u. We have a sine and we have a cosine. So maybe either one would be a valid u, right? Well, we could try each one and we would see that only one would work. Typically, what I like to say is we want the u, or what a lot of professors say is we want the u to be the more complicated one. That's what people will say. Choose the more complicated expression. And sometimes that will run students into trouble because the more complicated looking expression sometimes doesn't work. So like, for example, in the last one, maybe this z was like 3z plus 6, and this z squared was just a z squared. And so the 3z plus 6 looks more complicated than z squared. And so that's what people would choose. They would choose a 3z plus 6, but that's not at all what we would need to choose. So that's why it's important to recall for just regular power functions like this, that we need to choose the u to be 1 degree higher than the other one. But as a good rule of thumb for things that maybe aren't those functions, we do want to look at what the more complicated, quote unquote, more complicated function would be. And in terms of sine versus cosine cubed, it would obviously be cosine cubed. So we're going to want to do something with u here. And anytime we're looking to do a u sub, we never want to include the exponent as part of the u sub. We want to leave that because that's what we're going to use for the power rule. So the u is always just going to be the base function, and the exponent is just going to be there. So I'm going to choose u to be cosine here. And again, I encourage you to use sine. Maybe try it out and see that it doesn't exactly work out so well. It may work. I don't know 100%. It may work. I don't think that it would work out quite as nicely. It probably would work though. So let's choose u to be the more complicated thing, which is going to be the cosine. If I say u is cosine of t, then du is the derivative of cosine, which is negative sine of t dt. Always make sure you remember the dt because that's what we have to solve for. So dt equals negative 1 over sine of t du. So what we need is this expression and this right here. And what that tells us is that this is equal to the integral of the sine of t over cosine. Remember that cosine cubed of t is mathematical shorthand for cosine. What the heck did I just write? Cosine of t quantity cubed. So this is more of what we should think about when we're doing this. So now that we know cosine of t is u, this is just u cubed. But dt now is this right here. So minus, and I'm going to put parentheses because make sure that this is a negative and not trying to subtract the value. Negative 1 over sine t du. And once again, if we have any t's left that don't cancel out, we've done something wrong. What we notice is that sine over sine will cancel. There's still a minus, so make sure that you carry the minus along. So minus the integral of 1 over u cubed du. But you can't integrate a fraction like that unless it's 1 over u, in which case it'd be the natural log of the absolute value of u. So this is the negative integral of negate the exponent, bring it up, u to the minus 3 du, which is equal to the negative fraction bar u up a power gets more positive. So this is minus 2 over minus 2 plus c. All right, let's kind of adjust this a little bit. Minus times minus is positive. So I'll write this as 1/2, 1 over 2, maybe, well, we're not looking to plug anything in. So this is actually okay. So 1 over 2, u to the minus 2 plus c. But once again, we're not looking at things in terms of u for the original equation. We're looking at it in terms of t, which is our u value up here, cosine of t. We'll plug that back in. This is 1/2 quantity of cosine of t to the minus 2 plus c. And this is what our integral would look like. All right, here's another expression. So this one may look similar to things that we've done before, but what you notice is when we integrated them before, it was maybe the numerator and denominator switch. So it was like maybe regular x minus 1 over x, and you were able to take the denominator and split it into two different terms and then simplify it. And then you had 1 plus something else, and then you were able to integrate. But you notice because this is under a square root and you have multiple terms, you can't do that. And so we have to do something else. What you also notice is that there's no one term that has a higher degree than the other, which may present with a problem initially. But what we do see is we have two terms that have the same degree, which does help us. So this is what you should take from this. If you have any two terms with the same degree, or alternatively, any two terms that are like the same, so like if you have two natural logs or two of anything, this is the construction that you're going to want to have for this specific question. So you're going to want to take the most complicated looking thing again and call that your u, because they'll have the same degree, so you can't choose like that. So take the most complicated looking thing. Again, don't bring the exponent along for the ride. So we'll choose u to be x minus 1. Now, if we try to just use this, we can say du then is the derivative of x is just 1. So that's 1 dx, so I don't necessarily need to write the 1. So du just equals dx here. So these two things are very important. But now, if you notice, and I try to plug it in, this is equal to the integral of x over, this, remember, is to the 1/2. So x minus 1 is u, so this is u to the 1/2. Dx is just du, so I can say du. But I can't integrate this because I have an x here, and I can't integrate when I have two variables. So I need to find an expression to plug in for x. If I have two things that are the same, and I let u be one of the things, the more complicated looking thing, I can solve for x just by using algebra. If I add the 1 to the other side, what I get is that x is equal to u plus 1. Now I have an expression for x in terms of u, and I can plug that in. So this is actually the integral of u plus 1 over u to the 1/2 du. Well, now we're in business. Now we have that situation that I mentioned earlier where you have a single term on the bottom, and we can split it up. So let's do that. This is the integral of u over u to the 1/2 plus 1 over u to the 1/2. Put parentheses around it and du. U to the 1 minus u to the 1/2 is the integral of u to the 1/2, because 1 minus 1/2 is 1/2. Plus this you can just bring into the numerator by negating the exponent. So this is u to the minus 1/2 du, and we can now integrate. So we have a fraction bar u up a power, 1/2 plus 1 is 3/2. Divide by that power, 3/2, plus fraction bar u up a power from 1/2, 1/2 plus 1 is 1/2. Divide by that power, 1/2, and then add c because this is indefinite. We'll once again adjust these because they're complex fractions. When you divide by a fraction, it's the same thing as multiplying by the reciprocal. And so instead of dividing by 3/2, we'll multiply by 2/3. So this is 2/3 u to the 3/2 plus 2 over 1 is just 2, u to the 1/2 plus c. Now the last step, again, we didn't have it in terms of u to begin with. We had it in terms of x's. U equals x minus 1, so I need to plug in x minus 1. So this is actually equal to 2/3 x minus 1 to the 3/2 plus 2, x minus 1 to the 1/2 plus c. And I can guarantee you 100%, if you looked at that question, you would not expect this to be the answer. So once again, if you see things that are 1 degree higher than the other, choose the higher degree to be your u. If you see things that are the same degree and you don't have anything else funky going on, choose the more complicated looking thing to be your u and then solve for the other variable. Plug it back in. If you see things that don't fit any of that, just choose the more complicated looking thing, try it, and if it doesn't work out, choose something else. A lot of this is just going to be trial and error, to be completely honest. Now, what about if we have a definite integral? Because now we've covered indefinite and definite integrals, so we can talk about both of them. And the reason why we have to talk about them separately is because they are two very distinct things. So we actually have two different methods of solving for definite integrals. I learned it one way. This is not the way that I learned it, but this is the way that the book does it. And it's a pretty straightforward way, so this is the way that I'll do it. So what this says is you're still choosing u to be g of x, the same thing that you did before. Find g prime that's continuous, and don't worry about that, just take the derivative of g. Now, this is the same setup from before, right? You're finding some function in terms of g of x where you still have a g prime. This is what we were doing. But this is the difference. So for a definite integral, we don't have to re-plug in for g of x when we're done. What we do have to do to account for the fact that we are changing g of x to u, to a function of a different variable, is we'll change our bounds. And so what I mean is we'll change the bounds from a to plugging in a into our u function that we just created. And that's the new bound for our, not denominator, it's not a denominator of an integral, just our lower bound of our integral. Same for the upper bound for our b. We'll plug b into our g of x to get the upper bound of the integral. I will again note if in this kind of a situation, there is a very good chance that when you change your bounds, you may get bounds that have a higher one on the bottom than the top. And so you will have to negate that. And then you can flip your integral because you can't evaluate that if you don't do it like that. All right. So this is the way that you want to do that. If you are curious about the way that I mentioned, if you don't like this way, I'm not going to do any like this. So if you are curious at all, I know it's kind of towards the end of the semester at this point when you're watching this. If you are curious, you can reach out and I'd be happy to tell you. But essentially the other way is if you kept it in terms of a to b and did f of u du, what you would have to do after that is say that this is, well, I guess I don't need to change that right now. You would need to integrate, and then what you would need to do is you'd say this is f of g of x evaluated from x equals a to x equals b. So you notice that change is that instead of saying the integral with respect to u, you'd plug back in for g of x, and then you could evaluate using the bounds you started with. So if you don't want to change your bounds, just plug back in like we were doing for this right here. If you were given that this is from, say, 0 to 1, you can use fundamental theorem of calculus part 2, use u sub, follow through, plug back in, and then plug in 0 and 1 if you want. Otherwise, you can just change the bounds using the way that I mentioned. We're going to use that way for this. Again, if you want to learn the other way, feel free to reach out and I'd be more than happy to explain it. All right, I believe that we only have 2 examples left, and then that's the end of your semester besides the final and the rest of your homework. So let's go ahead and evaluate this right here. So now we're looking to evaluate a definite integral, and we have this crazy looking function. We again see this to the 5th power, so we're not going to try to distribute that in any way because we don't want to sit here for 30 minutes. So we notice that we have things in terms of just x's. We will want to first identify if we have one degree that's higher than another degree. We see that here we have an x squared, and here we have an x cubed. So we do have something that fits the u sub rule, where we choose u to be the thing with the higher degree, and in fact, it would be the entire quantity, because again, if you just choose one, it doesn't work. So u is 1 plus 2x cubed. Once again, we don't include the exponent because we need that for the integration. Therefore, du is the derivative of this. Derivative of 1 is 0. Derivative of 2x cubed is going to be 6x squared, but then dx, because we have to indicate that we took the derivative. And then we'll solve for dx. So dx is going to be 1 over 6x squared du. So these are the two formulas that we're going to be using. But now to plug back in, what we have to do is we have to change our bounds. And so here's our u function. What we have to do is we have to evaluate at 0 and at 1. So u at 0 is just plugging in 0. So that's 1 plus 2 times 0 cubed, which is just 1. And then u at 1 is 1 plus 2 times 1 cubed. 1 cubed is 1, times 2 is 2, plus 1 is 3. So these are our new bounds. So this is lower, this is upper. So this is actually equal to the integral. So the 0 turns into a 1, and then the 1 turns into a 3 of x squared. We said the 1 plus 2x cubed is the u. So this is u to the 5th. Dx we solve for to be 1 over 6x squared du. And we'll once again make sure that things cancel out so that we only have things in terms of u. And we see we have an x squared here over x squared here. Those go away. We do keep the constant though. So this is, I'll pull the 1/6 out of our integral, the integral from 1 to 3 of u to the 5th du, which is 1 over 6 times. And then we can just use the power rule for this. So this is u up power is 6, divide by that power is 6. And now, similar to when we were using the fundamental theorem of calculus part 2, you do not add a plus c because you're going to get a number. We're evaluated with bounds. So what we are going to do is we are going to put parentheses and we're going to put an evaluation bar and we're going to put from 1 to 3. It is very important that you change your bounds if you're planning on leaving your u in. If you don't want to change your bounds, this would be the step where you plug back in for 1 plus x cubed for your u, and then you can plug in 0 and 1. This eliminates that step. So let me combine this first. This is 1 over 36 u to the 6th quantity from 1 to 3. And what we get, I'm just going to give you, because this is not a fun computation, is going to be 182 over 9. And again, if you're doing something, maybe on an online homework, the numbers might be funky. You might have to use a calculator. But on any sort of an exam in my class or future math class, at least at UAlbany, you are not allowed to use a calculator. And so you would be given numbers that maybe would be a bit more manageable than trying to plug in like 3 to the 6th, then divided by 36. Oh, let me specify one more time why I got this number. So what this comes from is 1 over 36. I plug in the 3 first, 3 to the 6th, but then I have to subtract when I plug in my lower bound. So this is 1 over 36, 1 to the 6th, which gives me this right here, the 182 over 9 when you simplify it. So we always plug in your upper bound first. This is the fundamental theorem of calculus part 2, upper bound first, subtract, plug in your lower bound first. Make sure you use parentheses so that you're not subtracting just the first term and you're subtracting the whole quantity instead. All right, this is your last example of the semester, and then we are done. So let's go ahead and finish it up. Use substitution to evaluate the integral from 0 to 1 of x times e to the 4x squared plus 3 dx. Obviously, this one looks way different than the ones we've done so far. We again want to first see if we can use a regular rule that we've learned so far. We see x times some function of e, and so we should immediately recognize that we cannot. This is a product of two things. We can't distribute our integral, so therefore we have to use some other method. Obviously, the other method that we have is substitution. So that's the way that we're going to have to use. So we'll evaluate what we have here and ask ourselves, do we have one function of x that is 1 degree higher of the other function of x? We see we have a plain old x to the first power here, and e doesn't really matter so much. We have a 4x squared plus 3 here. This is 1 degree higher than this. Therefore, that's going to be our u. So choose u to be 4x squared plus 3, which tells us that du is the derivative of this. That's 8x. The derivative of 3 goes to 0. Dx, because we took the derivative. We'll solve for dx. So dx is 1 over 8x times du. So this is what we need, and this is what we need. Now we can go ahead and find our new bounds. So we have u of 0 equals, so we'll plug in 0. 4 times 0 squared is 0, plus 3 is 3. U of 1 equals 4 times 1 squared plus 3 is 4 times 1 plus 3 is 7. So our new bounds are 3 and 7. So this is equal to the integral. So again, the 0 here, as you see, goes to 3. So we'll put a 3 down here. And the 1 here goes to 7. So we'll put a 7 here. X will stay. E to the, well, we said 4x squared plus 3 was u. So this is u. And then dx we solved to be 1 over 8x times du. We'll once again see that we have two x values here. They do in fact cancel when you do x divided by x, and the 1 over 8 has to stay. And so this is the same thing as 1 over 8 times the integral from 3 to 7 of e to the u du. Now we know that the derivative of e to the u or e to the x or anything like that is just that thing, right? If you have something else in the exponent, then we have to do something different with it, but just simply e to the u would be e to the u. So because the derivative of e to the u is e to the u, the integral of e to the u is also just e to the u. So that tells me that this is 1 over 8 times e to the u, evaluated from 3 to 7. Now all we have to do is plug in. We always want things to be in the most exact form, like the simplest, most exact form. And so that means that we're not, obviously, again, we can't use a calculator, so we're not going to plug anything in. E is an irrational number, so if you tried, you'd get some irrational decimal. So just plug in the value. So this is 1 over 8, e to the 7, minus 1 over 8, plug in the lower bound, e to the 3. E is a number, to a number is a number. You can't do anything with these two things, so this is your final answer. All right, so that is it. We are officially done. You are done learning. You have finished all of your lectures. Congratulations. I apologize if some were too long. I apologize for some of the mistakes that I've made along the way. I like to think that they were a learning experience, but you know, it is what it is. I hope I made up for it by explaining how I went wrong and how to correct a thought process like that. If you have any questions at all, still feel free to reach out to me. Again, I, at this point, don't know any of you, but I'm sure by this time at the end of the semester, I will know many of you. So it has been a pleasure working with all of you. I wish you all luck on the final, and I wish you all luck in your following semesters, whether that be here or at a different school. All right, bye guys.